Hello.
Hello.
Kannan sir.
Arul?
Sir, can we start or shall we wait for another 2 minutes, sir?
It's up to you. Because whatever the one you are telling, you are going to tell, I am going to follow that. That's all.
Okay, sir. We'll wait for another
It's
2 minutes,
according to you.
sir.
Yes. Yeah,
Yes.
yeah. Yeah. I don't have any issue.
Okay, sir. Okay.
Arul. Arul?
Sir?
I need a feedback from the students at the end of the class. Maybe if they are going to give I don't want their name. Okay. Just
Okay.
what is their expectation? Okay. At the time of starting the session, what is their expectation? At the end, how much they have received it? If there is anything for improvement and
Okay,
all,
sir.
I need.
I will.
Hmm.
Yes, sir.
So
Yes, yes.
collect everything. So if you can give it to me, next thing I can change. And also, even in future also, if I'm going to present it to someone else, okay, I can change accordingly.
Okay, sir. I will collect it and mail it to you, sir.
Yeah, it's okay. It's fine.
Yes, sir. Sir, we can start the session, sir. In due time,
Okay.
other students will also join the session, sir.
Yeah. No.
Yes, sir. Good afternoon, students. Today, we are going to have a session on aerospace propulsion, and our today's guest is Dr.R.Kannan. He is an assistant professor from Amirtha Vishwa Vidhyapeetham, that is in Coimbatore, a very esteemed institution. So you can practically talk to him, and you can easily gain more knowledge from the professor. And as you heard by yourself, he requires a feedback, so which means you can simply talk to the professor and gain whatever doubts you have, you can ask him. And if you have any comments, you can directly tell the professor as well as you can tell it to me. Okay. So from this 4 to 6 2 hours, you will be having you will be entertained by Professor Kannan. If you have any doubts regarding your propulsion or thermodynamics, you can simply ask him regarding gate. Okay, sir. They are all yours. You can start the session, sir.
Good afternoon to all of you. So basically, I'm alumnus from IIC and IIT. I'm PhD from Indian Institute of Science, Bangalore, Aerospace Department, and Masters from IIT Kanpur, Aerospace. My field of interest is aerospace propulsion, and experimental aerodynamics. Okay, that's my focus. After my PhD, I was in University of Toronto as a postdoctoral fellow. So right now I'm working with Amirtha. So I had around more than 10 years of teaching experience. Especially I trained students for gate preparation. So with my own academy also, I did that. So this, I think this session will help you. Means whatever the experience I have gained over the period of time, I'm going to share it with you. So I'm taking aerospace propulsion, rocket propulsion for my own students in Amirtha, and also I had taken a class outside also. So if you had any question, don't hesitate to ask me. I'm ready to clarify that. See, my policy is something different. If you are going to ask something, I'll say that if I know the answer, I'll say okay. If I don't know, I'll refer and tell you. Even if I don't know, you go and get it from somebody else. That's my policy. So don't hesitate to ask any question. Okay. So let us go ahead with that. So now in this session, we are going to talk about that your gas turbine. Okay. So prior to that, your basically the gas turbine, you can have your power generation also, and your aircraft propulsion device also, aerospace aircraft propulsion device also. So now prior to go into the your aircraft propulsion devices, we are going to classify generally how your types of propulsion systems and all. Okay, so we are going to talk about that. Okay. Types of propulsion devices. Okay. In general, your aerospace propulsion devices, we are going to classify that air breathing propulsion and non-air breathing propulsion. Non-air breathing propulsion. You know that, okay, your air breathing propulsion means, okay, so whatever the propulsion devices, okay, the propulsion devices are going to take oxygen present in the atmospheric air for the combustion of fuel. Atmospheric oxygen present in the atmospheric air. Okay, so that's going to be used for the combustion of the propellant. But in the case of a non-air breathing propulsion, you have to carry a separate oxidizer and as well as fuel along with you. Then only you can have a generate a heat energy. Okay. So I'll come back to that your non-air breathing propulsion. Okay, I'm going to talk about very briefly about non-air breathing propulsion. So if I'm going to handle your rocket and space rocket propulsion part, then I'll talk about that more in detail about that. Okay. So air breathing propulsion, first we can have your reciprocating type and your non-reciprocating type. Non-reciprocating type. So in the reciprocating type, okay, we know that, okay, your SI engine and your CA engine. That is your spark ignition engine and your compression ignition engine. Okay, so these are the two types of that. Okay, earlier if you look at that first generation aircraft after the First World War or Second World War, people are used your SA engine propeller driven piston engine aircraft and all they are used for propelling that one. So after that Frank Whittle's innovations, so people moved towards your jet engine and all. Okay, so one is going to be working with the Otto cycle, another with the your diesel cycle. Okay, so those things and all you might have studied in your thermodynamics. If you don't know about that, just to go refer your thermodynamics. Okay, air standard cycles, try to understand Otto cycle and your diesel cycle, have a more clear idea about that. What is your difference between SA engine and CA engine, how they are going to different and all, just look at that. maybe I have another one more session next week, another 2 more sessions next week, okay, Tuesday and Thursday again. So if you need anything, just email it to me. I can I can help you in resolving that. You can get my email ID from your class instructor. Okay. So next is your the non-reciprocating type. What we are going to do is we are going to have a gas turbine, ramjet, scramjet, and your pulse jet. Okay. So if you look at that, okay, the gas turbine and the gas turbine is going to be further classified as your turbojet, turboprop, turbofan, and your turbosoft. So here we'll be having an thrust automatic device, okay, afterburner. Sometimes if you look at the fighter aircraft and all, they will be going with a turbojet with afterburner or a turbofan with afterburner. Okay, so that also can be included as your types of gas turbine. I'll come to that your gas turbine part. If you look at that, okay, your gas turbine part, okay, what is going to have, okay. I'm not going to talk about that anything on the power generation. I'm going to talk only in terms of your aircraft propulsion devices. Okay. So now, if you look at that, the gas turbine, okay, what will happen? And your intake is going to be there. Afterwards, your compressor, your combustion chamber, your turbine, and then you have a propelling nozzle. This is basically a simple turbojet. If you look at that. So turbofan, okay, prior to that, I'll talk about that, your turbofan configuration and other things and a little later. So these basically, if you look at that, the gas turbines are going to have a rotating components like, it's going to have a rotating components like your gas turbine is going to have a rotating component such as, okay, your turbine and compressor. If you look at that, okay, the purpose of the compressor is going to be, it's for whatever the incoming air here, okay, it's going to have a Mach number of something close to a 0.8 or 0.5 or 0.6, whatever the air, okay. The purpose of the diffuser is going to be one role, and then afterwards, it's basically converting your kinetic energy into pressure energy. So basically, what we call it as a pressure recovery. And then further, whatever the air coming out here, okay, out of your intake, passing through that your compressor. So there your pressure of the gas is going to increases. Then the air is going to be passing through the combustion chamber. There you are going to spray your fuel. Then what will happen? The hot gas generated in the combustion chamber, they are going to expand over the turbine. So because of the expansion over the turbine is going to rotate, and turbine compressors are connected by means of a single shaft here. So turbine is going to rotate and compressor also going to rotate. So initially at the time of starting your engine, you need to provide a power to your compressor for rotating it, for establishing the hot gas, okay, that is going to expand over the turbine. The moment your turbine starts rotating, okay, you can disengage whatever the power you are going to provide into your compressor. So they are going to have a sustained motion. After the expansion, still the air is going to have whatever the hot gas is going to have energy, thermal energy as well as pressure energy. They are expanding through your propelling nozzle. You are going to get your thrust. So through that only you are going to. Basically, your compressor is for the pressurization. But if you look at that, your ramjet and scramjet, even pulse jet, you can't see any rotating component. No rotating components like compressor and turbine. Okay. So there is no rotating components like a compressor and turbine. In the case of a ramjet, scramjet, even pulse jet also. Okay. So what is happening is, okay, I can show you that, okay, how it is going to be. If you look at that, your ramjet, okay, just a supersonic one. So it's going to have a normal shock formation, oblique shock formation. Okay, your Mach number is going to be greater than 1. So automatically that while passing through your oblique shock followed by a normal shock, okay, you are going to achieve a pressure rise, what we call it as a ramp compression. So the pressure rise is going to occur in the case of your ramjet, scramjet as well as pulse jet. They are going to achieve through your ramp compression mode. So then how come you are going to travel? So if you look at that, your ramjet, the static thrust is going to 0. Normally, if you keep it in the ground, if you start rotating the compressor, you are going to establish the flow. But you can't. If you want to start your ramjet, you need a rocket or a gas turbine or something. You need that for starting your ramjet. Okay. So in the ramjet, the combustion is going to be in the subsonic mode. Combustion takes place subsonic mode. In the scramjet, combustion takes place in the supersonic mode. Okay, supersonic. Okay. So these are the main difference between gas turbine and ramjet and scramjet. Okay. So ramjet is going to be, the combustion is going to be subsonic mode. Scramjet, the combustion is going to be a supersonic mode. Okay. So these are the your general classification about the propulsion devices used in the aircraft. Mainly, this is going to talk about that your air breathing propulsion. This non-air breathing propulsion is nothing but your chemical rockets and non-chemical rockets. Non-chemical rockets. Non-chemical rockets. Okay. So these are your this one you need to know. Any question here, sir? If you have any questions, you can raise or you can ask me, because we have only limited students, so we can have a discussion here itself. Do you have any questions, sir? Don't hesitate. I told you about my policy. Okay. Any question? Okay. Then I move ahead for your next part of it. Okay. Okay. So now, if you look at your, let us take your simple gas turbine. Okay. Simple turbojet. Okay. Let us take this as A, this is a 1, this is a 2, this 3. I am marking a station for that, 4, and you are 5. So basically, this is a schematic of a simple turbojet. Schematic diagram of a simple turbojet engine. If you look at that, okay, your A to 1 is nothing but your intake or a diffuser. Intake or diffuser. Your 1 to 2 is your compressor. And your 2 to 3 is your combustion chamber. And 3 to 4 is your turbine. And your 4 to 5 is your propelling nozzle. Basically, it's nothing but your convergent nozzle. Okay. In the case of your gas turbine and all, we'll be having a convergent nozzle. Okay. So let us look at that. What is going to happen in the case of your intake? Okay. So this is your intake. Here, what is happening is, okay, whatever the incoming air, okay, your whatever the with the flight velocity, if it is a flight velocity something close to a subsonic compressible mode or something subsonic incompressible mode, your flight is going to travel. Okay. For example, let us take a Mach number 0.8. It's going to be something subsonic compressible mode. So whatever the kinetic energy, that is air, that is going to have a certain kinetic energy. Kinetic energy means it's going to be a mv square by 2. Okay, that's your kinetic energy. So that's going to be converted as a pressure energy. That is a pressure recovery. So here, so it's a diffuser is nothing but a diverging cross section. Diverging cross section. So here your kinetic energy is converted as a pressure energy. Kinetic energy is converted as a pressure energy. Okay, so what we call these phenomena as a pressure recovery also. We even treat pressure. Okay. So next is, if you look at that, okay, this is A to 1. So let us look at that next 1 to 2. In the 1 to 2, what we call it as, it's a compressor. Okay, it's going to be a compression process, means increasing your pressure. Increasing the pressure. So two ways of we used to say that. Okay, normally in the case of ideal cycle, we are going to treat that as an isentropic compressor, or otherwise, okay, in the case of ideal sense, ideal assumption, ideal cycle assumption. But in the case of okay, if you are going to consider the losses, okay, we are going to treat that an adiabatic compressor. Okay, so adiabatic compression in the case of your, if you consider losses. What do you mean by an isentropic process? An isentropic process, okay, it's nothing but, okay, an isentropic process, an adiabatic reversible process. Adiabatic and reversible process. You might have studied in your thermodynamics. Reversible process. So adiabatic process means there is no heat addition. Addition or rejection from the system. Heat addition or a rejection from your system. And your reversible process means it will come back to the original, the process is come back to the original state without leaving any traces, without leaving any traces. Okay. So that's what you are, okay. For example, if I am going to some other place, okay, I am not going to leave any traces over there. So that's a thing, we will call it as a reversible process. Okay, if one satisfies that, okay, both, okay, isentropic process. Normally people used to ask you to, okay, even in your this one and all, ask you to compare your isentropic versus adiabatic. So for that you need to answer this one. So here what is happening is two types of compressors are there. Okay, earlier days compressor and all. Okay, in the mainly in the aerospace propulsive cards, centrifugal compressor and axial compressor. In the case of a centrifugal compressor, an impeller will be there. Okay, it's a rotating component. A rotating component. Whatever the incoming air, the kinetic energy is going to be increased. Incoming air, kinetic energy is increased. Kinetic energy is going to be incoming air, kinetic energy is going to be increased. So, and also they are going to be, the direction is going to be, the axial direction is going to be changes in the radial direction. Axial direction, the incoming axial entry, changes to radial outlet. Okay. So then what will happen? There will be a vent space or a diffuser passage will be there. Through the diffuser passage, okay, diffuser passage, the increase in kinetic energy is converted as a pressure energy. Increase in kinetic energy that happened in your impeller is converted as a pressure energy. Okay, so here the impeller is going to increase the kinetic energy of the incoming air, and it's changing your air direction from the axial entry to your radial entry. That's what you might have seen that. Okay, your air is going to be enter at the center of that. If you look at the centrifugal compressor, air is going to be leave along along the radial direction. Okay, so the air is going to enter here and going along that one. And here in the impeller, your kinetic energy is increased because of the rotating motion, and the increase in kinetic energy is going to be converted as your pressure energy. That is, pressure recovery is going to take place in your diffuser passage, band passage. Okay, that is going to be having this is a stationary passage. So through that, okay, this is a way we increase this one in the centrifugal compressor. But in the axial compressor, what will be having is, okay, we'll be having a rotor plus stator. Rotor plus stator. Okay. In the case of a rotor, what will happen? It's a rotating component. A stator is a static component. So here the direction is, air direction is, okay, whatever the incoming air, the direction is not going to change. Air entry direction, air direction of your air flow won't change. So here we are going to increase the kinetic energy. In the case of a rotor, in the stator, we are going to convert the kinetic energy into a pressure energy. So depending on your pressure requirement, you are going to have a more number of stages. If you look at that modern day compressors fixed with, modern day gas turbine engine fixed with the axial compressor, if you look at that 16 stages, 21 stages. But if you are going to keep on increasing the number of stages, automatically what will happen? Your number of stages are, if the number of stages are going to increase, automatically weight of the engine will go up and the complexity will go up. So normally they will optimize that depending on your pressure requirement. Okay, how many stages and all that. So afterwards, what will happen? With the help of your compressor, you are going to pressurize that, your whatever incoming air. Then, okay, your Next is your 2 to 3, your combustion chamber. 2 to 3 is your combustion chamber. So if you look at that, the combustion chamber, okay, your air is going to enter with the CPA, your M dot A with a temperature of T02. So there you are going to spray the fuel. So what will happen while going out? Okay, the hot gas will be coming out. Okay, that with the temperature of T03, and your fuel flow rate is M dot A plus M dot A. This is what is happening. Okay, so here we are going to have a constant pressure heat addition. Constant pressure heat addition in the case of your combustion chamber. So I come back to the operating cycle. There you are going to get even more. So again, your 3 to 4 is your turbine. Your compressor and turbine is connected by means of shaft. Okay, whatever the hot gas, okay, expanding over the turbine, expands over the turbine. So it's going to provide a work to compressor operation, because compressor and turbine are connected by means of a single shaft. Basically, if you look at that, okay, your turbojet engine or a gas turbine engine, matching of compressor and turbine is going to be a critical issue. Okay, so if you are not going to match your speed versus your this one properly, automatically that leads to failure of the engine. Okay. So here a stator followed by a rotor. In the case of what we call it as a nozzle guide vanes, we will call it as NGV. So if you look at that, okay, this is your axial turbine. What we call it as this one is nozzle guide vanes, or we'll say that simply as a stator. This is going to be a rotor. Okay. Next is your 4 to 5 is your propelling nozzle. If you look at that, okay, it's basically the propelling nozzle is going to be a convergent cross section, convergent passage. So what will happen? Your thermal energy is going to be converted as your kinetic energy. Your thermal energy is going to be converted as a kinetic energy. Okay, so this is a simple turbojet, the components of a simple turbojet. Okay, so these are your functions of each and every component. Functions of each and every components. Okay, so if you look at that, okay, in ideal sense, okay, the operating cycle for your gas turbine engine, operating cycle for your gas turbine engine. Let us take a TS diagram. Okay, for ideal cycle, isentropic compression, constant pressure heat addition, and isentropic expansion. A to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. So A to 1 is your intake, 1 to 2 is compressor, 2 to 3 is constant pressure heat addition, 3 to 5 is your turbine expansion, isentropic expansion. That is A to 1 is, and isentropic compression. 1 to 2 is again same isentropic compression only. 2 to 3 is constant pressure heat addition. 3 to 4 is an isentropic expansion. Same way, your 4 to 5 also your isentropic expansion. So these are this is for the case of an ideal cycle. If you look at that, okay, for a real cycle, okay, means not real cycle, ideal cycle with losses, okay, your 1 to 2, sorry, A to 1, A to 2, pressure loss will be there, and this is what it's your A to 1, 1 to 2, 2 to 3, 2 to 4, and 5. So this is your what we call it as your delta P. Okay, A to 1 is adiabatic compression, 1 to 2 adiabatic compression, your heat addition with the constant pressure with losses. Okay. 3 to 4 is isentropic, sorry, adiabatic expansion. 4 to 5 also adiabatic expansion. Any questions, sir? Any question? Sir, please open your mouth. If you are going to ask any question, then only you are going to learn something out of it. At least say that you understood that. Otherwise, there is no point in saying it from my side, and I don't want to go ahead like that. Any question? Just go through that once. Okay. You might have scribbled something, or if you have any question on that, please tell me. I'm ready to clarify that. You take a couple of minutes time. Yeah, it's good. I got a first response. Continue. If you have anything, even you can type it in your comments column also. I'm ready to means down. I'm ready to answer with that. Keep in mind that at the end of your 4-hour session, not today, next week, okay, I'll conduct a test. Keep in mind that. At least you are going to answer for that. You are going to ask question for that, at least for that. Do you want me to conduct a test or not? So, prepare so sincerely. Tomorrow, if there is a 3-4 marks or 5 marks, if it is going to be there in this propulsion part, whatever the portion I am going to cover, if it is there, I am also going to be happy, so happy. If you are going to get that 4-5 marks. Okay, so then I'll move ahead further. Okay, so now we have seen that what are the functions of your each and every component. Okay, right now I did it for your turbojet. Okay, so we similarly you can do it for your turbofan also, turboprop also. Okay, I'll come back to the turbofan and turboprop little later. Okay, how? Just I'll give a glimpse here. Okay, if you look at that turbofan, after that, okay, after the intake, you are going to have a fan. So then you are going to have a compressor. So here in the case of a turbofan, okay, first is your again your A 1, 2, 3, 4, 5, and 6. So your A to 1 is going to be your intake. 1 to 2 is your fan, and your 2 to 3 is your compressor. 3 to 4 is your combustion chamber. 4 to 5 is a set of turbine. Okay, and your 5 to 6 is going to be a separate nozzle for a cold flow and hot flow, or otherwise a combined nozzle, propelling nozzle. So the advantage of here is going to have if you look at the turbofan, you are going to get a hot thrust and cold thrust. So whatever the one from the bypass, okay, these one. So whatever your flow through that bypass passage, okay, that's going to generate your cold thrust. And because whatever the air that is passing through your fan here, okay, that's going to be pressurized, and they are going to exhaust through a separate nozzle, or okay, after it's going to mix with the turbine exhaust of hot gas. So then the hot thrust is going to be whatever your air through the compressor, combustion chamber, and turbine, and then your propelling nozzle. This is going to be contribute for your hot thrust. So the advantage of your turbofan engine, okay, you can reduce the noise of that. Reduce the noise produced by the engine. Second thing is you can increase your propulsion efficiency. Okay, so that is the advantage. But in the case of a turboprop, what will happen? Okay, you are going to have a propeller. It's going to be with in addition to your turbojet, simple turbojet configuration. So that's what. Okay, so in the turbojet configuration, okay, simple turbojet is going to be connected to this one. So this is going to be having a highest propulsion efficiency, even better propulsion efficiency. So if you look at the propulsion efficiency, okay, the order of decreasing propulsion efficiency, if you look at that, the propulsion efficiency is going to be, okay, it's going to be highest for your turboprop, and next is your turbofan, and next is for your turbojet. So thrust is going to be your reverse of that one. So turbojet is going to be having you can produce a higher thrust, turbofan, and your turboprop. Even the operating altitude also going to be different in the case of your turbojet and turbofan. Okay, so these are the part of that. Next is, okay, we'll go ahead for before next our aim is we need to estimate the performance parameter for your simple turbojet engine. Simple turbojet engine. Performance parameter means your thrust or specific thrust, your TSFC, your propulsion efficiency, thermal efficiency, and yeah, your fuel air ratio, those things. Okay, we need to estimate. So that's the aim of that. For doing that, what we are going to do is, for example, you take a, let us take a simple turbojet. So before going into that simple turbojet, if you look at that, a compressor, a combustion chamber, and your turbine. These three units are called as your gas generator. What we call it as this one as your gas generator in the channelized. Because what will happen? Whatever incoming air pressurized, and we are going to burn the fuel with the help of whatever the air present here. Okay, air pressurized air coming out of the compressor. They are going to expand through your turbine. So this, it's basically these three units, what we call it as a gas generator. So now, okay, we are going to have let us have a compressor, your combustion chamber, and your turbine, and also let us take a simple turbojet. So we'll follow the same station number A21, 122, 223, 324, and your 425. Okay. So I don't want to explain more on that. What is that? So first is we need to look at the component performance. Component performances. See, if you look at that, your thrust relation, it's going to be m dot A plus m dot F into VE minus m dot A into VA plus PE minus PA into AE. This is your thrust relation for your turbojet engine, simple turbojet engine. Okay, so m dot A is mass flow rate of the air, mass flow rate of the air. This is mass flow rate of your fuel. PE is your exit velocity. VA is your flight velocity, and your P is exit pressure at that is at this point. Okay, your exit pressure, that is your P5. Okay, exit pressure, and your PA is the atmospheric pressure. AE is the exit area. Okay, so this is your thrust relation. So now, if I want to estimate all those things, I need to know your VE. So the VE is going to be, if I know all those your station, your variable, it's going to be 1 to 1 related. So first is, okay, if I want to get your thrust value, that is your TSFC value. Okay, everything, if you want to get it, so you need to know every component performance and how the parameters are going to change at the exit. Okay, we need to see that. First, let us finish that your each and every component performance. That is, we are going to look at the thermodynamics of each and every component. Basically, your diffuser, your compressor, your combustion chamber, turbine, and propelling nozzle. Okay, we are going to club together. We are going to solve the performance parameter for your turbojet, even by adding your fan thermodynamics. Okay, we are going to get the performance of your turbofan. Same way we'll do it for your propeller, include propeller, get the performance parameter. It's basically we are going to have a simple subroutines we are going to develop. Normally you might have studied in your C language or whatever your programming language. So you might have talked about that your subroutines. Okay. Same way we are going to develop a subroutines for each and every component. That is, we are going to look at the each and every component performance, and at the end we are going to look at that your overall performance of the engine. Okay. So first is our main attention we will give it for your turbo machinery first. Turbo machinery means it's going to be nothing but your compressor and turbine. Even your fan also going to be included. Okay. Right now we will focus our attention towards your turbo machinery. Okay. So in the thermodynamics, okay, you might have studied engineering thermodynamics. Engineering thermodynamics, you might have studied about open system, your closed system, and your isolated system. Okay. In the open system, okay, if you look at that, the region of interest is going to be, we are going to take it as, if it is a region of interest, we are going to take it as a system, and the location other than system means area, region other than the system, we are calling it as your surrounding. The thin layer that is separating between system and surrounding, it's called as your boundary. Okay, so I'm not going to talk too much about that. Okay, your boundary. Okay, so now across the boundary, if you have if you have both mass as well as energy transfer, mass and energy transfer, then we call that as an open system. So in the case of a closed system, we are going to have only energy transfer across the boundary. If you look at the isolated system, neither energy transfer nor mass transfer. So now let us look at that your gas turbine here. So I had given what is the definition for your open system, closed system. You are going to treat it as an open system or a closed system or an isolated system. Any one of you can say something? What will you say? Whether it's a open system or a closed system or an isolated system, your gas turbine. Excuse me, sir. You will call your gas turbine as an open system or closed system or an isolated system. What is happened? Just if it is an open system, across the boundary, there will be both energy as well as mass transfer. If it is a closed system, across the boundary, only energy transfer. If it is a closed isolated system, neither energy transfer nor mass transfer. I need an answer from you, sir. Quick, sir, quick. Okay, so if you look at that, your gas turbine engine, so see here, let us take this as your boundary. This is your boundary. This is a boundary. So what will happen? Your mass is entering, your mass is going out. You look at that energy also. So we can call this your gas turbine as your what we can call now. Now can you say that it's going to be a open system? we are going to treat that as a open system. Your gas turbine as a open system. Okay. So if you go back to your thermodynamics again, okay. So there for an energy equation, whatever the energy equation from the your first law of thermodynamics, okay, your first law of thermodynamics, okay. So you look at that energy equation for open system. For open system. Yeah, simplified one. I'm going to take it as I'm not going to do any complex analysis and all right now. Okay, that's going to be H1 plus m v1 square divided by 2 plus mg is at 1 plus your heat supplied. Okay, that is going to be equivalent to your H2 plus m v2 square by 2 plus mg is at 2 minus ws. Or whatever the one. Okay, let us take it as a plus ws. So we will talk about that work done on the system or work done by the system. We will divide it. Work done on the system, work done by the system. Okay, we will be taking it as a little later. Whether it's okay, those things that we will consider later. Little later. So this is your energy equation. Yeah, for a open system. Let us go back to our gas turbine. Aircraft gas turbine. So what are we going to treat here is first is okay, the change in your potential energy is neglected. Change in potential energy is neglected. First thing. Okay. So what will happen now? H1 plus m v1 square by 2 plus qs is equal to H2 plus m v2 square by 2 plus, let us take it as a ws. We'll come back to that whether that's work done or work done by the system little later. Okay. Let us take a plus or minus. We'll put a plus or minus. Now, okay, we've taken a gas turbine. Now we are going to look at the component performance. Okay, individual component we'll be looking at that. Let us take your compressor and turbine. Compressor and turbine. What I am going to do is, okay, even the ideal cycle or with the ideal cycle, isotropic actual cycle with the actual cycle, okay. So we are going to treat the process in adiabatic process. So automatically what will happen? Your QS is going to be 0. So what will happen now? V1 square by 2 is equal to H2 plus m V2 square by 2, okay, plus or minus ws. You got it now? Okay, now we are going to look at that. Here I forgot to mention one. This is going to talk about that. This is your even I can put some color, it's better. This is your static enthalpy. This is, it's going to talk about your kinetic energy. This is your potential energy. This is going to talk about that heat addition or a heat rejection. Same thing is going to apply for H2 and this one. This is going to be, WS is going to be soft work. Okay. So now we look at the change in potential energy is 0. First is okay for a aircraft gas turbine engine. Okay. So then we are going to treat the for a compressor and turbine. We are going to have it as a your flow as an adiabatic flow. We are going to assume it as an adiabatic flow. So we can write it. So divide that okay by a specific form. Your okay your small h is specific enthalpy. Your capital H divided by m. So your H1 divided by M. Okay, H1 plus V1 square by 2 is equal to H2 plus V2 square by 2 plus or minus Ws by M. Okay. Now here we are going to look at that. Now we have seen that this is going to be a specific static enthalpy. Now, how can I get the your stagnation enthalpy? So here, if you are going to decelerate the flow, because stagnation means it's going to be in the state of a rest. Okay, in the state of rest, whatever the enthalpy of the medium in the state of rest. Okay, so adiabatically decelerate the enthalpy at a point where the flow is decelerated adiabatically to zero velocity. Decelerated adiabatically to zero velocity. So this is called as your stagnation enthalpy. Even we will be calling it as even we will be talking about that in coming slides. We are going to talk about that stagnation temperature. Okay, the temperature at a point. Where the flow is decelerated adiabatically to zero velocity. So there is a difference between your stagnation temperature and stagnation pressure. If you look at that, your stagnation, your pressure there, okay, that means your stagnation here also it's going to be zero. So here the pressure at a point where the flow is decelerated isentropically to zero velocity. Flow is decelerated isentropically zero velocity. So keep in mind that they asked twice in the gate examination. Define the stagnation pressure, stagnation temperature, and all twice. Okay, I know I have seen the question paper. I have seen the previous papers. So you need to know. Okay, define the stagnation pressure. They had given a 4 answer. So mainly you have to know that. Okay, the flow is going to be decelerated isentropically to zero velocity for getting the your stagnation pressure. But if it is for a stagnation temperature, the flow has to be decelerated adiabatically to zero velocity. You know what I mean by isentropic process? It's going to be a adiabatic as well as reversible, your isentropic process. Okay. So now we'll go to your equation. Okay. For compressor and turbine, H1 plus P1 square by 2 is equal to H2 plus P2 square by 2 plus or minus Ws by M. So we can write this one as a flow velocity is going to be 0, H01, H02 plus or minus Ws by M. So what will happen? Okay, your Ws is equal to, okay, your H02 minus H01. Your plus or minus, right? Yeah. So we can write it as, okay, even we can write Ws is equal to your H02 minus H01 plus or minus. So this one is going to talk about the soft work. Okay. So for a compressor, it's you are going to work done on the compressor. So it's going to be a negative sign. For turbine, okay, work done on the it's going to do work. Okay, your turbine is going to do work. Okay, so that's going to be positive in the case of a turbine. Okay, in the case of your compressor, okay, you are going to have a work done by the system for compressing that part. So negative side for a compressor, it's going to be negative, and for the turbine, it's going to be positive. Okay, same way for the your WS is for your turbine. Okay, your software for the turbine, it's going to be your H03 minus H04. This is for turbine, and this is for your compressor. Okay, the sign is going to change, negative sign, minus WS is equal to your stop. Okay, your soft work is going to be H02 minus H0. So now, while writing your soft work, normally we have written that, okay, if you look at your book, okay, we'll be writing your MCP into T02 minus T0. So how did we get that? We have to know about that now. How can I write that? Okay, your H0 as a your enthalpy as a, how can I write that as a your MCP T02? How can I write H01 as a MCP T01? How can I write that? How can I write your H is equal to CPT? We need to know about that. So first let us finish that part, okay? Then we'll go to the your or otherwise, okay, let us finish the your diffuser part, okay? And let us look at the your diffuser and your nozzle. Again, okay, I'm going to take it as a your H1 plus M V1 square by 2 plus QS, because already we have assumed it as no potential energy. Okay, your H2 plus your M V2 square by 2 plus WS. So in the case of your diffuser and nozzle, no soft work. No soft work. So automatically your WS is going to be 0 here. So, and also we are going to treat the flow as an adiabatic process. Your QS is going to be 0. So we are going to have a H1 MV1 square by 2 is equal to H2 plus MV2 square by 2. So we can write it as this as a your H1 plus V1 square by 2 is equal to H2 plus V2 square. That is your your H01 is equal to H02. Your enthalpy is going to be, stagnation enthalpy is going to be constant for the two states. So we are going to use that, okay, in further cases and all. I'll tell you how we are going to club it together. Okay. Okay. Let us look at that, how we got the your H is equal to CPT. Okay, and U is equal to CVT. Okay, U is nothing but your internal energy. Your H is your, that is specific internal energy. Your H is specific enthalpy. So here, okay, we are going to come across your perfect gas. So what is your perfect gas equation? P is equal to rho RT. So normally, if you look at that, whatever the gas, it's going to have a degree of freedom. The gas is going to have a certain degree of freedom, depending on whether the gas is going to be a monoatomic, diatomic, and triatomic. So whether the gas is going to be monoatomic, diatomic, or triatomic, based on that, your degree of freedom is going to vary. So 3 translation plus 3 rotation. That's your totally 6 degree of freedom. So if we are going to say a gas as a perfect gas, then you have to treat, it has to satisfy a condition of, okay, it has to be a calorically perfect gas, and thermally perfect gas. It has to satisfy both of the conditions. Thermally perfect gas. In the case of your calorically perfect gas, okay, you know about what we mean by CP, that is specific heat at constant pressure, and your CV, it's going to be specific heat at constant volume. Okay, so if your CP and CV are constant, we can treat the gas as a calorically perfect gas. When the CP and CV, if they are going to be function of temperature, then we will call that gas as a thermally perfect gas. Okay, if your CP and CV constant, we are going to say that the gas is a calorically perfect gas. So when it is going to be possible? If you look at the working medium temperature is something close to 800 Kelvin, we can treat the gas as a calorically perfect gas. If it is more than 1000 Kelvin, we are going to take the gas as a thermally perfect gas. So most of the time we assume that working fluid as okay for a simplicity purpose, okay, working fluid as here in the case of a gas turbine, we are going to assume it as a calorically perfect gas, or if it is more than that, okay, hot gases and all, we are going to assume that here CPG, okay, we used to give the value of CPG and CP, okay, those things, gamma G and all. Okay, so we will see that. Okay, so here, how come I can write H is equal to C, U is equal to CVPP? So if you look at that, your whatever your perfect gas, the working fluid. Okay, so here what is going to happen is, okay, that is your specific enthalpy, that is your H, your specific internal energy, that is U. We can write it as a function of, okay, a state variables, function of state variables. What do you mean by state variables? It's going to talk about that a state of a system. For example, I have a beaker and I'm going to put it in the water. Okay, put a water. If I'm going to heat it, what is the state of this one initially? Okay, if I'm going to cool that one, it's going to be ice. So there we are going to talk about that your pressure, temperature, and your specific volume. If you are going to heat it up, okay, we are going to talk about that its state in terms of your pressure, temperature, and specific volume. If it is going to vaporize us, we are going to talk about the pressure, temperature, and specific volume. So those things are, we call it as your state variables. So H is equal to, I can write it as function of pressure and temperature. U, I can write it as a function of V and specific volume and temperature. So using partial differentiation, I can write is equal to your dH is equal to dou H by dou T at constant pressure dt plus dou H by dou P at constant temperature into dt. Same way du also I can write it as dou U by dou T at constant volume into dt plus dou U by dou T at dou U by dou V at constant temperature into dt. So this is a partial differentiation, we can write that. Okay, so now if I am going for a constant volume process, so what will happen? My du is equal to, this term is going to be 0. Okay, so dou U by dou T at constant volume into dt. So this one I can write it as CV into dt, where your CV is equal to dou U by dou T at constant volume. Same way, I can go for a constant pressure process. A constant pressure process. Okay, so where I can write it as, okay, dH is equal to dou H by dou T at constant pressure into dt. I can write this as a Cp into dt, where your Cp is equal to dou h by dou t at constant pressure. So now I have a two relation, du is equal to Cv dt and dh is equal to Cp dt. So now we go for a calorically perfect gas assumption. If you go for that, I'm going to have your U is equal to CVT, because Cp and Cv are going to be constant. H is equal to CPT. So now if you look at that soft work for your compressor, I can write it as M Cp T02 minus T01. Or okay, you look at that, your H1 plus M V1 H2 plus M P2 square by 2. Okay, even we can write it as a H naught for the compressor and diffuser. Okay, I can write it as this one as a your CPT1, because M is going to cancel out. Your V1 square by 2 is equal to CPT2 plus your V2 square by 2 is equal to CPT.
Boys, can you hear me? Am I audible to you? நான் பேசுறது கேக்குதா? அருள்மொழி பேசுறேன்பா. You can reply. Is the session over? Boys, is the session over or is there any network issue? Okay, boys, he's coming back. It seems we have another half an hour. Please talk to him as much as possible. Okay, we will talk after he completed this session. Okay. Professor, your voice is not audible, sir. I think you have to unmute
Yeah, yeah.
your.
Sorry. So I can write my, okay, your CPT, this one as CPT plus V square by 2 is equal to CPT naught. Okay. So this is a generalized relation. Okay. I can divide by CP. So I can write T plus V square by 2 CP is equal to T naught. CP is nothing but, okay, your gamma R by gamma minus 1. CV is equal to R by gamma minus 1. Your CP minus CV is equal to R, and your gamma is equal to CP by CV. And also another one more thing that you have to keep in mind, that your A, that is your speed of sound, it's going to be gamma RT. So here you keep in mind that your R here, whatever the one is mentioned, is not a, is a gas constant. So normally we used to make a mistake. So your R is equal to R bar divided by your molecular weight. So R bar is the universal gas constant, and that is 8314 joule per kg Kelvin. Whatever the medium that we are going to have, we can get a molecular weight of that if you substitute. For example, and all air and all, your R value is going to be 286 or 287 joule per kg Kelvin. You are going to get that your molecular weight something close to 28. We substitute it. If you divide that, you are going to get that. So keep in mind that while finding the speed of sound, you have to apply a proper R value. Otherwise, your data is going to be wrong. If they are going to, sometimes they will ask, okay, they will ask you to find out a speed of sound in the medium that's going to cover CO2 or argon. So there you have to use 8314. You need to use a molecular weight of your CO2, get the value of your R, then you substitute it here and find out your A, speed of sound. Keep in mind that. Okay, so I don't want to extend prolong for us lots of time. I need means discussion from your side. Do you have any doubts? Anything? Let us discuss. Okay. Sorry. Any questions, sir? Any question? Take 1 or 2 minutes time. Any question? So don't hesitate to ask question. I don't have any problem in answering it to you. If you are going to get clarified now itself, I can give an assurance. Okay, surely you can get 4 5 marks. Or wherever you go for an interview or written test, ISRO test or anything, you can answer this. Anyway, okay, we'll go ahead further. Okay, now we almost we looked at that how you are from the thermodynamics aspect. We looked at that how your soft work and all. We are good. Already you might have studied these things in your thermodynamics, but okay, you need to know about that perspective of your gas turbine perspective. So next is okay. If you look at your simple gas turbine, okay, already we have seen that. Okay. Okay, 1, 2, 3, 4. So right now, what we'll do is we'll focus on 1 to 4. Already I told you, okay, your gas generator, okay, your gas generator. Okay. That is, it comprises of compressor, combustion chamber, and turbine. Okay. So right now we'll go for a first initially compressor and turbine. Compressor and turbine. So what is it talking about? That first is we are going to look at that isentropic efficiency of your compressor. First we will focus on that your isentropic efficiency of the compressor and isentropic efficiency of the turbine. Then we will go for a polytropic efficiency. Initially we will solve that one everything with the isentropic efficiency. Then we will come back again for a polytropic efficiency. I will explain to you what it means by polytropic efficiency while going further. Okay. So your isentropic efficiency of the compressor, okay, it's basically a ratio between, okay, your isentropic work transfer to actual work transfer. Isentropic work transfer to actual work transfer. Okay. Now we can ask why we went for your work transfer and all soft work and all. Now we know that, okay, your MCP, your what is the station here? T02 minus T02 dash minus T01 divided by MCP actual T02 minus T02. The prime means it's going to be T02 dash means it's going to talk about that your isentropic. Okay, so this is going to be your isentropic work transfer. This is your actual work transfer. Okay, so now what is going to happen here? I can write it as your isentropic efficiency or that T02 dash minus T01 divided by T02 minus T01. Normally, while solving your problem, they are going to give your isentropic efficiency. And also, if you look at that, if your aircraft is going to operate with a certain Mach number and your PA operating altitude, you can calculate your your P0A and your P0A, and from the isotropic efficiency of your diffuser, you can get your T01 also, T01 and your P01. So those things we can calculate, okay, easily. We will while going for your diffuser, you will be understanding more on that. So let us take a T02 minus T01, okay, is equal to isentropic efficiency into T02 dash minus T0. Sorry, 1 by isentropic efficiency. So now what I can do is I can take a plus by P01, I can write it as P02 by P01 whole to the power your gamma minus 1 by gamma. So here your P02 by P01 is nothing but okay, it's your compressor pressure ratio. So normally from these, okay, at the end of your compressor, okay, we can get the P02 value and T02 value. In addition to that, your T02 minus T01 value. What is the input condition at the entry? Okay, we can get the your diffuser entry to the compressor. We can provide your T01 value, your isentropic efficiency of the compressor, and your compressor pressure ratio. That is your P02 by P01. So normally they are going to give your P01 value, your isentropic efficiency, or if they will be giving input, from that we are going to find out these values. Okay. So now this is for the your, even if I want, okay, you want to find out your soft work for the compressor, okay, we can do that. Okay, if you know the mass flow rate, okay, m dot Cp T02 minus T0. If someone is going to ask you to find out that, okay, you can find out that. And also keep in mind that the isentropic efficiency formula, once I think once they have asked isentropic efficiency of the diffuser, they had given the relation, they'll ask you to pick up which one is the correct one. So just to keep in mind that your relation for the isentropic efficiency of the your compressor. Basically, this is the isentropic efficiency of So basically here what is happening in the case of a compressor, it's a compression process. But while going for a turbine, okay, what is going to happen? This is an expansion process. It's going to be reverse of that, okay, what we'll be calling it as an isentropic efficiency of turbine. So that's going to be equivalent to your, okay, your actual work transfer divided by isentropic work transfer. Actual work transfer divided by isentropic work transfer. So this is going to be, if you are going to simplify that, okay, you are going to have a T03 minus T04 divided by T03 minus T04 dash. So we are going to have a your T03 minus T04 only. We need to get that. Okay, that's going to be your isentropic efficiency time T03 minus T04 dash. So normally we will be getting a your T03 is nothing but your turbine inlet temperature. Normally, most of the cases they will be giving it turbine inlet temperature. So that's going to be, okay, your isentropic efficiency T03 1 minus your T04 dash by T03. So what we can write it as, okay, this one as NT T03 into 1 minus one minus 1 by, okay, your T03 by T04 dash. Okay. So further we can write it as isentropic efficiency T03 1 minus 1 by P03 by P04 whole to the power gamma g by gamma g minus 1 by gamma. This is for your turbine. Any questions, sir? Sir, it's very, very important. If you have any question, please now itself clarify, because it's going to be part of your performance analysis. Okay, so then only one thing, with that I will stop the class here. Okay, so you take your combustion chamber now. So what is there? Your m dot, okay, a CPA T naught 2, is it right? Yeah, T naught 2. Okay, you are going to spray the fuel. That's going to have a your m dot f, and that's going to have a certain calorific value. So outlet m dot a plus m dot f CPG and your T naught 3. So do energy balance m dot a CPA, okay, T naught 2 plus whatever the m dot f into your calorific value of the fuel equal to m dot a plus m dot f into CPG T naught 3. So now if I am going to divide that whole equation by m dot a, and your CPA T naught 2 is equal to m dot f by m dot a into calorific value of the fuel is equal to 1 plus m dot f by m dot a CPG T naught 3. Okay. So this one I can write it as CPA T naught 2. So here I am going to define F, okay, that is F is, okay, your m dot f by, that is fuel to air ratio, fuel to air ratio, UCV equal to 1 plus F into CPG T naught 3. So now what will I have, okay, if I am going to rearrange these, take F this side, F into FQCV minus F CPG T naught 3 is equal to CPG T naught 3 minus CPA T naught 2. So I can write F is equal to CPG T naught 3 minus CPA T naught 2. Okay. Here QCV minus CPG. This is the your fuel to air. So if you know that, okay, you can find out your gas centrate properties at the exit of the gas centrate. Just you look at that construct one by one, you can easily find out this one. Any questions, sir? I'm not going to discuss more on that because I'm exhausted. Any questions? Arun, ask your students to talk.
Hello.
No, உங்களுக்கு ஏதாவது தமிழ்ல கேள்வி கேட்கிறா இருந்தாலும் ஏதாவதுனா ப்ராப்ளம் இல்லைன்னா கேளுங்க, ஒன்றும் பிரச்சனை இல்லை. உங்களுக்கு இங்கிலீஷ்லாம் கேட்கணும், ஏதாவது ஹெசிடேஷன் இருந்துச்சு அப்படின்னா நீங்க தமிழ்ல ஏதாவது தெரியலன்னா கேளுங்க, நான் ஆன்சர் பண்றது கிடையாது. So if you don't have any question, then we'll stop the class here. We'll go for our own purpose. Okay. What I'll do is whatever the lecture I have taken. Okay, I have written my whiteboard. Okay, that is scribbled in my OneNote. Okay, I can convert these as a PDF kind of thing. Okay, export it as a PDF. I'll send it to your sir. Okay, he will share it with you. Uh, Maybe if you have any questions, you can come back to me. My email ID is okay. Uh, RRSKannan at gmail.com. RRSKannan at gmail.com. My number is 999-437-5658. Okay. So if you need any other advice for your gate class preparation or any other technical support you want, you can approach me. I'm ready to help you in that. Okay. If you want anything, even other than your if any subject doubts or anything, so my area except structures and stability and control, I can handle for you. It's not an issue for me. So you can approach me. You can get it clarified. rrskannan@gmail.com and my number is this is you can even this with the 9943756. It's with the WhatsApp also. You can you can discuss with me. It's not an issue for any of your needs. Anything specific? So please share a feedback about this lecture. So I can improve first of all. Second thing is I can give a next time I can give a better lecture. If there is anything negative aspect of it, I can correct it. I can give a better lecture. Uh, I can set right some of my issues. Okay. Yeah,
Sure,
that's
sir.
all.
I will collect the feedback from them and I will consolidate and I will mail it to you, sir.
Yeah. Yes, sir. I'll send that this one immediately right now. The whatever the one as a
Yes, sir.
PDF one. So it's going to be useful for them
Yes,
also
sir.
because
Mm.
even
I
if they
will
have any
get it from you and I will
yeah
post it in the
yeah
Google Classroom for them, sir, so
uh,
that they can use it.
uh, yeah surely. Even at the end of that, what I'm going to do is what I'm planning is I thought of conducting a one test also. You can I share the question paper with you. Let them look at
Okay.
that. Let them
Okay, sir.
try to answer for
Yeah.
that. And if they have any question, let them. You can, even after later period also they can message me also. It's not a problem.
Sure, sir. Sure, sir.
Okay.
If that is all, we can wind up the session, sir.
Yeah, we can wind up. I don't have any issues.
Okay, sir. Thank you, sir.
Thank you.
Thank you
Thank
very
you.
much for your valuable time, sir.
So next
Thank you,
we
sir.
will plan again on Tuesday again, next Tuesday. Okay.
Yes,
Thank
sir.
you.
Yes.
Thanks.
Okay. Boys, you're there. 71, roll number 1932, Kalaikovan.
Yes, sir.
You can talk to me.
Yes, sir. Hello.
அத்தனை நாட்டி கேட்குறாரு யாரோ ஒருத்தர் ஏதோ பதில் சொல்லிக்கலாம்ல. ஒரே நிமிஷம். I'll stop this meeting. I mean, I'll stop recording this meeting. Okay. இல்லாட்டி, can you give a feedback about the session directly now? Hmm? You have anything? Problem ஏதாவது போட்டாரா கண்ணா அவரு சாரு? கேட் ப்ராப்ளம்ஸ் ஏதாவது? நிதிஷ், அனுஷா மாலினி, அபிஷேக், கலை. Literally very poor attendance, yeah. You know how much they are charging for this 1 hour? It's a great amount of money that we are spending, the government is spending for you. Abhishek, roll number 1, Abhishek.
Sir,
What do you feel about the session, Kana? அவர் ஏதாவது ப்ராப்ளம் ஏதாவது போட்டாரா?
derivation போட்டாங்க சார்.
ஃபுல்லாக டெரிவேஷன் தான் போட்டாரா?
ஆமாம் சார்.
அப்போ நீ எம்ஹெச்ஆர்டியில் ப்ராஜெக்ட் ஏதாவது பண்ணுறியா என்ன?
ஆமாம் சார்.
ஓகே சார், நீ அதுக்கு வந்துடுவே அப்படின்னு சொன்னார் சரவணகுமார் சார்.
இல்லை சார், இனிமே தான் சார் அதுக்கு மீட்டிங் இருக்கு. 6:30 மேலே தான் சார் மீட்டிங்.
எத்தனை மணி? ஓகே, என்ன பண்ணுவீங்க அதில்? ட்ரைனிங் மாதிரி கொடுப்பாங்களா அதுக்கு?
இன்னும் அவங்க இன்னும் ஒன்றும் சொல்ல சார்.
அபிஷேக்,
அவங்க இன்னும் ஒன்றும் சொல்ல சார். அதில் ஏதாவது கரெக்ஷன்
ஓகே
இருந்துச்சுன்னா
ஓகே
மாற்றி தரேன்னு சொன்னாங்க சார்.
ஓகே. ஓ, இன்னைக்கு போனாதான் தெரியுமா?
ஆமாம் சார்.
ஓகே, ஃபைன் ஃபைன். கலை கலைக்கோவன் தானே பேர்? ஏப்பா நிதிஷ் இருக்கானா? இஸ் நிதிஷ் ஹியர் நவ்? ரோல் நம்பர் 71, ஃபைனல் இயர், ரோல் நம்பர் 71.
Sir,
ஓகே, who's 71?
sir, Ovia, sir.
நிதிஷ் வந்து 70 இல்லையா?
Yes, sir.
ஓவியா, நிதிஷ் வந்து 70 இல்லையாமா?
ஆமா சார்.
71 அவன் நினைச்சிட்டேன். நீங்க 4 செஷன் அட்டன் பண்ணிருக்கீங்கன்னு நினைக்கிறேன்.
ஆமா சார், அட்டென்ட் பண்ணிருக்கேன் சார்.
ஐ மீன் ஸ்டெபிலிட்டி அண்ட் கண்ட்ரோல் அட்டன் பண்ணிருந்தீங்க.
ஃப்ளைட் டைனமிக்ஸ் அப்புறம் இந்த கிளாஸ் சார். 4 செஷன் அட்டென்ட் பண்ணேன் சார்.
ஓகே ஓகே, வெரி குட்.